Hello friends, here's a quick overview of pressure volume graphs and isothermal processes and something called an isotherm, which is just a dotted line on the graph. Here we go. So if we look at a simple process where we have an initial pressure of 101,000 pascals, atmospheric pressure, and a volume of 10 liters that is expanded to a volume of 15 liters via heating. Where the temperature increased from, let's say, 300 Kelvin to temperature 2, well, the ratio has to be the same. This would be 450 Kelvin. So immediately I would write down things like this. Delta T is positive. 450 minus 350, 150 Kelvin. Delta V is positive, 5 liters, which is, careful, you need cubic meters, 5 times 10 to the negative 3 cubic meters. Subtracting the liters first is probably a good idea, and then converting to cubic meters by just dividing by 1,000. You can do decimals if you like, but I'm going to do scientific notation. I would write that down first. You can also do things like this. Delta KE total is what? It's heated. Sorry, just because it's heated, careful, doesn't necessarily mean the temperature went up. The temperature went up because the temperature went up. Delta T is positive. Let me write it like this. Delta T is positive, temperature goes up. Work is the second. Work is negative P delta V is what? Well, this is an expansion. So this is actually losing energy because expansion. The molecules are hitting an expanding wall, losing energy. You can think of it as them pushing on the wall, therefore giving energy to the outside system. They're losing energy in that process. Either way, expansion is a negative value, which means Q is positive. Let's say this does it as a constant pressure. Sorry, I should have mentioned that. Constant pressure. This is an isobaric. Isobaric heating, which is also an expansion, because we need a flexible container to do this. So if we heat a flexible container, it'll expand. Due to the increase in pressure, the expansion will then decrease the pressure to keep it constant. Cool. Because heating. Or because it needed to be heated to overcome the negative work. So we can solve for these as we've done in class, and I'll leave you to do that on your own, but this is the analysis. What I want to focus on is graphing this. This is pretty simple, don't overthink it. Pressure versus volume ends up showing us these processes wonderfully. So the pressure is 101,000 pascals. I can just label that here. You can make this ATM or pascals. I like it in kPa. Kind of depends on the situation. The point is, in this case, it doesn't change, so it almost doesn't matter. Here, the volume went from 10 liters to 15 liters. Again, you can have your axis be in liters, cubic meters. I'll keep it in liters. Switch to cubic meters if you like. Again, that's up to you. As long as you're consistent in a given situation. Don't switch mid-question, right? And you do need this for the equations. So even though your graph may be in liters, you need cubic meters for instance, plugging it in here. You need cubic meters. Right? Anyway, so the graph is pretty easy. Here's my point 1. Careful, P1, V1 is here. Just find those 2 points. That's point 1. Point 2 is same pressure, but increased volume. Point 2 is there, and you draw a line. Careful, the line's important. Going from point 1 to point 2, and I draw a little arrow. I tend to fill my arrow in, but you can just do an arrow, as long as the arrow is clear on which direction it's going. So this is expansion. Isobaric. That's what it looks like. Pause and make sure that that makes sense. Constant pressure, increase in volume. Don't overthink it, but make sure you can do it. Next one. Pause that if you need to go back. Let's do an isochoric, right? A rigid container. If I heat a rigid container, or maybe we'll cool one. Let's cool a rigid container. Let's say pressure 1 is 101,000. T1 is 300 Kelvin. And the volume is, let's say, 2 liters. It's V1. Let's keep it the same because it's a rigid container. Cool it down to, let's pick an easy number, 150 Kelvin. So that's cold. So the pressure will drop by a half to, what is that, 50.5 kPa. If that makes sense, I did that kind of quickly, but you can figure that out. From this, you can figure out the number of moles. Of course, PV equals nRT. We'll solve for moles to get delta KE total equals 5/2. If this is air, this is for air, which is N2O2. 5/2 NR delta T will get you that. Great. You need this first, and you plug that in here. You're fine. Typically, I might give you the number of moles, but it's all good. Either way, I'm focusing on the graph. So you can do your delta KE total analysis, your work analysis. Here, the work is 0. Delta KE total here is negative because delta T is negative. Work is 0 because delta V is 0. It's neither expansion nor contraction. It's isochoric. And heat is therefore negative because cooling. And in this case, Q equals delta KE total. Great, let's graph it. So here I have constant volume of 2 liters. Careful, pressure is on this axis, volume's on this axis. Sorry if I didn't emphasize that. Pressure, I'll do kPa. I'll start it out at 101 and go to 50.5. I'll just label 50 and maybe 100 there. But it starts at 101. Oh, I like my other color. Process 1 here. P1 equals 101 kPa. That's stage 1. Stage 2 at the same volume is P2 equals 50.5 kPa. You don't actually have to label this, but I'm just reminding us that it's these exact values, although I may be labeling my axes differently. That's kind of up to you how accurate you want to be in that. But either way, it goes down from point 1 to point 2. This is isochoric cooling. Isochoric cooling, same volume, rigid container, but it drops in pressure due to the slower speed of the molecules. Slower collisions and less frequent collisions. It's both of those combined that will lower the pressure. This is isochoric. So I can fit that in there, cooling. Let's get that. So that's a vertical line down is isochoric, horizontal line is isobaric, right? Constant vertical axis is a horizontal line, constant volume is, sorry, it's a horizontal line, constant horizontal axis volume is a vertical line. You can just see that, right? What about isothermal? So what if neither are constant? Let's do it in general. So PV equals nRT. So if T is constant, by the way, how we need to do this physically is, for instance, the balloon expanding was isothermal, where the work is negative, and we actually needed Q to be positive to overcome that. So the total change in energy, as we're going to find, is 0. Don't overthink that. If that doesn't make sense, we're going to review that next week. It's okay. But I'm just letting you guys know that's how expansion would work in terms of these. The point is, all you need to think about now is that T is constant. And N is constant. Let's just say it's a sealed container and R is constant. So these are all constants, which means P equals nRT over V. These are all constants. Which means if I'm going to graph pressure versus volume, pressure goes as 1 over volume. P1 V1 equals P2 V2 is how you'd solve for it. But how do you graph that? Well, you guys might remember a y equals 1 over x function. Looks like that. So it looks like this. And I'm going to do dotted lines. The reason I'm doing dotted lines is because it depends on what the temperature is. So if I have a hot temperature, they're up here. If I have a cold temperature, they're down there. In fact, I want to do that in a different color. Hot temperature. Cold temperature. Down there. So say this is 400 Kelvin. Then if you plugged in 400 Kelvin for here, you can test that in a graphing calculator on Desmos if you like. Sorry, I'm not going to do that in this video. Pick n equals 1, a constant n. R is 8.31. Say t is 400. You graph it, it looks like that. Change t to 300. They will not overlap. It'll simply be almost a parallel curve, if that makes sense. A parallel curve meaning they won't intersect. Parallel meaning they don't intersect. That's what I'm using that word to mean that. Say this is 200 and this is 100. The point is they're going to be non-intersecting curves that are an inverse function. But that makes sense, right? It's that simple. These are called isotherms. Lines of constant temperature. That are inverse functions of pressure and volume. As P goes up, V goes down. Now you might notice if you have an isobaric process, an isobaric process goes between isotherms because it heated up one to the other. And an isochoric process goes either up or down. Let's do heating this time. If it heated, it's going to go to a higher, hotter temperature. Increase in pressure, same volume, higher temperature. Here, an increase in volume, isobarically, constant pressure, higher temperature. So isochoric, isobaric goes to a higher temperature in both, from a lower temperature to a higher temperature. You guys see that? So this is isobaric heating, which expands. And this is isochoric heating, which stays rigid, but the pressure goes up. Isn't that cool? Right, so we can show that. So every process moves between isotherms as it changes temperature. The only exception to that is an isothermal process itself, which I'm just going to draw. Say I have this. Say I have 2 isotherms. Say I have 200 Kelvin and 300 Kelvin. And let's say I have a process that goes from here to here, 1 to 2, and then it follows an isotherm, and then it goes from here to here, like that. I'm going to try to draw my arrows. Maybe it's better to just draw them not filled in, but and 2 to 3, and then 3 to 4. So this would be isobaric heating, which is expansion. I heat it up, the pressure pushes out, it expands to a higher volume. And then this is isothermal expansion. Ooh. Like the balloon. You know, we allowed the balloon to expand at constant temperature. So what happened here? Did the pressure go up or down from 2 to 3? Here I have P1, here I have P2, here I have V1, here I have V2, here I have V3, here I have P3. So here was isobaric, here was isothermal, the pressure went down and the volume went up. Yeah, see that? So V2 to V3, that increased volume and decreased pressure. Ah, isn't that cool? Take a second and let that make sense. And then of course, this one is isochoric cooling, where the temperature dropped. Notice it went down to another isotherm. So notice all the tools we have in our graph. We can read temperature by looking at the isotherms. We can read pressure, and we can read volume. So this one's isochoric cooling. It dropped temperature at a constant volume, lowering the pressure. That's it. So you can read this from graph. Now you should know that isothermal expansion increased the volume. And if you increase the volume, there's more space. Yes, that's different from the work is negative thing, right? So if I allow something to expand, the work is negative, separate idea, the pressure drops. So maybe I'll draw that, right? Expansion. V increases, two things happen. Two separate things happen. One, work is negative because of a collision with expanding wall. And two, pressure drops because more space and time between collisions. Notice that these have nothing to do with each other, except that they're happening both because volume increased. So volume increasing creates both of these simultaneously, but separately. They're completely independent. So V increasing does both of these separately, right? Now, obviously, if I'm adding temperature to counteract this, right, we get a isobaric process. So if I'm increasing temperature and volume, it's isobaric. But if I'm increasing volume at a constant temperature, it drops in pressure. Ooh, see if you can follow that on the graph. If I'm increasing temperature and volume, pressure stays constant. If I'm increasing volume, same temperature, pressure drops. Boom. There it is. Pause, rewind if you need to repeat, that's it. See you guys soon.